Hello everyone, my name is Khalid Taneji, and my project is about the development and synthesis and characterization of gadolinium-based MOFs as contrast agents. Medical imaging is an important tool in modern diagnosis because it allows internal tissues and organs to be visualized without invasive surgeries. One of the most widely used imaging techniques is magnetic resonance imaging or MRI, which is especially useful for soft tissue imaging because it does not rely on ionizing radiation. Metal organic frameworks or MOFs are promising candidates because they are crystalline porous materials made from metal ions or clusters connected by organic linkers. Their structure can be tuned by changing the metal center, organic linker, pore size, and surface functionality. In this project, gadolinium was selected as the metal center because of its magnetic properties, while amino-functionalized dicarboxylate linkers were used to form the framework. The aim of this work was to synthesize and characterize gadolinium based MOFs and study their structural, chemical, optical, morphological, and thermal properties as an early step toward evaluating their potential as MRI contrast agents. The synthesized materials were prepared through a solvothermal synthesis method. In general, this method involves dissolving the gadolinium salt and the organic linker in a suitable solvent system, followed by heating the mixture in a sealed vessel under controlled temperature and time conditions. After the reaction was completed, the solid mauve product was collected and purified. The washing step is important because it removes unreacted metal salts and excess linker from the surface and pores of the crystal. This step can be described as solvent washing. After washing, the samples were dried and then characterized using several analytical techniques. Each technique gives different information about the material. XRD techniques provide structural and crystallinity information. FTIR confirms chemical bonding. UV vis and fluorescence study optical properties. SEM studies morphology, and TGA evaluates thermal stability. FTIR here is used to characterize the functional groups. In Figure 2, when comparing gadolinium BDCNH2 and gadolinium BPDCNH2, both spectra show evidence of gadolinium carboxylate coordination. However, the peak position and intensities are different because the two linkers have different structures. Gadolinium BDCNH2 contains a shorter aromatic linker, while gadolinium BPDCNH2 contains a longer biphenyl linker with extended conjugation. For the FTIR spectra in Figure 4, this FTIR comparison confirms that the BPDC-NH2 linker is present in the synthesized MOF. The NH stretching vibration from the amino group are still observed in the gadolinium BPDC-NH2 spectrum, showing that the NH2 functionalized linker was incorporated into the framework. Moving on to the PXRD spectra, PXRD was used to compare the crystallographic features of gadolinium BTC-NH2 and gadolinium BPDC-NH2. The main observation is the diffraction peaks of gadolinium BPDC-NH2 shift to lower 2 theta values compared to gadolinium BDC-NH2. Scientifically, the shift is important because according to Bragg's law, a lower 2 theta angle corresponds to larger interplanar spacing or larger d spacing. This is expected for gadolinium BPDC-NH2 because BPDC-NH2 is a longer linker than BDC-NH2. The longer biphenyl linker expands the distance between the metal clusters, leading to a larger framework spacing. Now, for the gadolinium BDC-NH2 pattern shows sharp and intense diffraction peaks, especially at low 2 theta values. These sharp peaks indicate high crystallinity and good long-range structural order. The similarity between gadolinium BDCNH2 and the European BDCNH2 literature pattern suggests that the synthesized gadolinium BDCNH2 may have a related framework structure. The SEM images show clear morphological differences between the two synthesized MOFs. The top row corresponds gadolinium BPDC NH2, which shows larger faceted crystals with surface attached, smaller particles, and textured features. This morphology may be related to the longer BPDC NH2 linker, which can influence crystal growth and framework assembly. The bottom row represents gadolinium BDC NH2, which shows a different morphology with more compact particles, clusters, and rod-like features. Overall, the SEM results show that changing the linker from BDCNH2 to BPDCNH2 significantly affects the final crystal morphology. Moving on to TGA thermal stability. In the thermograms, for gadolinium BDCNH2, the weight decreases gradually over the temperature range, indicating continuous solvent loss and framework decomposition. For gadolinium BPDCNH2, the material retains a higher percentage of mass at elevated temperatures, suggesting improved thermal stability. The higher thermostability may be due to the extended aromatic BPDC NH2 linker, which can provide stronger structural resistance toward thermal decomposition. At very high temperatures, the remaining mass is most likely due to gadolinium containing inorganic residue. UV spectroscopy was used to study the electronic absorption behavior of the synthesized MOFs. The gadolinium BPDC NH2 spectrum shows stronger and broader absorption compared with the gadolinium BDC NH2. This is because BPDC NH2 has a longer conjugated aromatic system due to the biphenyl structure. Greater conjugation lowers the energy gap between electronic states, which can cause absorptions to extend towards longer wavelengths. This result showed the changing of the linker from BDCNH2 to BPDCNH2 does not only affect the framework structure, but also changes the electronic properties of the material. Fluorescence spectroscopy was used to investigate the emission behavior of the MOFs. Gadolinium BDCNH2 shows a strong, broad emission band in the visible region. This can be attributed to ligand-centered emission from the aminoterphthalate linker. In comparison, gadolinium BPDCNH2 shows a different emission profile, which is influenced by the extended conjugation of the biphenyl linker. The difference between the two spectra shows that the linker structure controls the photophysical behavior of the MOF. Coordination to gadolinium can also affect emission because of the framework. It restricts linker motion and changes the electronic environment of the ligand. In summary, gadolinium-based MOF materials were successfully synthesized and characterized using multiple analytical techniques. Overall, the results show that changing the linker from BDCNH2 to BPDCNH2 affects crystallinity, morphology, optical properties, and thermal stability. These properties are important because the final goal is to evaluate these materials as MRI contrast agents, where gadolinium coordination, framework stability, water accessibility, and particle behavior all influence contrast performance. Although the synthesized gadolinium of materials were successfully characterized using several techniques, further analysis is still required to evaluate their actual performance as MRI contrast agent. One limitation of this stage of the project was that the research timeline faced a temporary setback due to unforeseen external circumstances that affected research continuity. As a result, some planned contrast agent related tests could not be completed within the current timeframe. Nevertheless, this research will continue in the next stage of the project, with the aim of completing the remaining experimental work further investigating the suitability of the synthesized gadolinium MOFs as potential MRI contrast agent. Future work will focus on more direct MRI related analysis. This include measuring MRI relaxivity, targeted imaging, particle size and dispersion, and biocompatibility. Many thanks to Abu Dhabi University for hosting the undergraduate research competition, and to my university, Khalifa University, the chemistry department, for my supervisor and co-supervisor, Dr. Mohammed Anfas and Dr. Mariam Bilston, and for the PhD group, Fatma Alim, Khadija, Ahmed Irfan, and Lulu, and my friends. Thank you for your time and thank you for listening.